Welcome to APEC. It's July 10th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Remi Cornwall will discuss electromagnetic propulsion, including static E-cross-B devices in the Feynman disk. Sandy Kidd will discuss his extensive work in forced precessed gyroscopic inertial propulsion, and Mike Gamble will present a brief history of Boeing CMGs. After that, we're going to catch up with the latest research from the Falcon Space team and associates, and we'll be wrapping up the event with open discussion and ad hoc presentations. Okay, a couple of quick reminders. You can view conference replays, details, and speaker info on our website at www.altpropulsion.com. Please save your questions for the Q&A session after each presentation. Go ahead and type those into chat as we go, and we will go through chat as well as take live questions after each presenter finishes. So I am very pleased to introduce you to our first guest. Remi Cornwall is an alumni of UMIST Manchester and London University, having degrees and higher degrees in electronic, electrical, and information software engineering and physics. He spent the early part of his career in industry at blue chip companies, but devoted his spare time to problems in engineering physics, where he's acted as a troubleshooter to several companies, solving diverse problems in the annealing of metals, design of HV generators and medical equipment, as well as ignition devices, consulting in anomalous physics research and engineering. His research company is working on 3 projects at the moment: thermoelectric conversion with ferrofluids, secure communication by quantum entanglement, and novel forms of electromagnetic propulsion. So let's welcome Remi to today's call, and I will now hand it over to you, sir.
Hello, everybody, and thank you for turning up. As you've heard, I'm Remi Cornwall, and I've got a presentation for you. It's theoretical at the moment, linked up with well-known experimental results, and I'm just throwing this into the pot of ideas to say that I will do the homework first in terms of the theory base, or if you find something that's an exception to the theory base, explore it further, present your results to make sure you're not wasting your efforts, not tinkering and so forth. So let's go full screen now on 1 second. So if I share the screen, yeah, I'm going to focus on EM propulsion theory, and if there's a little bit of time, I might discuss the other projects. Now, the kind of things I like, obviously experiment is key in physics. You've got to have repeatable experiments and your theory base before you can sort of get into the applied science and the engineering aspects. So that's the kind of area I work in. Give me a phenomenon and I'll look at it, theorize in it, and do something with it. But if it's very apocryphal, you don't tend to stand much chance. But that's just my opinion, and that's not to dissuade anyone doing things which are right off the beaten path. You carry on doing what you're doing. Don't take my word for it. Okay. So let's go on to the second page now. So I've got a non-exhaustive list of candidates for EM propulsion. So ion propulsion, ferrofluid drive. Let's go from them one by one. So we know about ion propulsion. NASA are currently, and the Chinese are currently doing work in that. There's also ferrofluid. It's like the alternatives, like the electrical dual. So ion propulsion, you're dealing with things which are electrically charged. With ferrofluid drive, you're dealing with things which are magnetically charged. So things like superparamagnetic particles. It's very much like an inkjet printer, same kind of technology, and it can shove out at the exhaust, so you gain some impact. We've got photon rockets, which we know are just like a light source as your exhaust. Pair production, I don't think I made a slide on that, but I'll come back to that. The Lorentz force, or what you might call ampere forces. Einstein-de Haas effect, we'll come on to that. E-cross-B devices in general, and then the Feyman disk, which is another type of E-cross-B device. Now, I'm not really too concerned with the propellant-like devices, so things like ion propulsion and ferrofluid. drives don't really turn me on. So what I want to see in the future is that we maybe can just put a power source, maybe it might be nuclear, and we've got all the energy in the world to get anywhere we want to, at least in this solar system, yeah, or to the nearest star systems. Yeah, you're going to run out of propellant. So let's consider things which can work solely from your power source. So I'll move on to the next slide now. And this is just a quick talk about ion propulsion and how they sort of put a figure of merit on rocketry. They talk about specific impulse, which is just the thrust divided by the rate of mass out the back. Yes, and you can quote it this way: newtons per kilograms, or meters per second. You can say it works for meters per second. You just put mv divided by m, the rate of change of m, or you can divide it define it with the weight of the propellant expelled, and the units come out as seconds. Now, obviously, rockets fare badly. Turbofans are much better because you're hauling a whole load of air, which is free. It's just around you. Now, ion engines, the selling point is to have a very high exhaust velocity. So they currently have the best specific impulse of current technology. So if we look at these graphs, if we look on the one on the left there, if you have a quick look at those, you can see ion engines at the top at the moment. So you've got electric propulsion there, magnetic. Are you seeing my cursor move around as well? Are you? Yeah, not yet. That's great. That's great. Okay, so have a quick scan of that. I'm not going to spend too much time. Let's move on to the other graph. That's propulsion performance. So a specific impulse again versus Mach number. So you're seeing that obviously turbofans, great big huge hunking things on current airliners. Down at the left-hand side, slow speed devices, moving on to ramjets, and then you're moving on to scramjets. So that's all very conventional. Good people working on that, but we want to break the boundaries, don't we? We don't, we just copy what everyone else is doing. Let's move on to the next slide. Okay, a photon rocket. You've got radiation pressure. You can see that things in things like the Crookes radiometer. You put that in sunlight and it will spin round. And we all know about comet tails as they go around the sun. The tail points away from the sun. So it's the radiation pressure. The relativistic equations describing this, just down here, describing how the energy of a body varies with the speed, the momentum, and you can just get a simple relation between these. And that's useful. Moving on to the photon rocket, you just take the ultra relativistic case. So you just set V equal to C there, and you get the usual ultra relativistic ratio. And that's the limit of it. If you're expelling things out the back, yes. But although it has the high specific impulse of C, it's very feeble. You're looking at 1 Newton per 300 megawatts, which is an extraordinarily huge amount of energy just to get a 1 Newton shove. So let's move on to the next slide and see if there's a way of doing things better than this. So I'm not going to upset the boat, rock the boat by believing that you can break things like conservation of moment energy, which is a portmanteau of conservation of momentum and conservation of energy. Yes, because they're very, very deep principles in physics, which we know are obeyed at least locally. Maybe not globally. You might have heard me a few weeks ago saying that there was this dirty secret in physics regarding conservation of energy in general relativity, but that's legerdemain stuff. Let's not talk about that. But there are very good reasons why you have conservation of momentum and conservation of energy. Now, it's all very technical stuff, but one can explain it intuitively. They talk about Lagrangians and Hamiltonians and making infinitesimal changes, translations, rotations, and so forth. And it so turns out that conservation of energy, effectively, it means that energy is a constant of motion of a system. So when you describe a system by its equations, you get this constant of motion, which doesn't vary with time. And what it's saying, intuitively, what it's saying is saying that the constants of physics don't change. Yes. So your gravitational constants, your electrical constant, and so forth. What it turns out that momentum is saying, and angular momentum, that what they're effectively on an intuitive level, they're saying that space is the same everywhere. It's homogeneous, and it's the same in any direction. It's isotropic, right? Respectively. So linear and angular momentum are saying that. Now, moving on to the next one. The problem that people will have there, where it will beg a belief, if someone says they've made a drive which violates conservation of momentum, because of the synergy of those in relativity, they're two bites of the same cherry. They're joined together in relativity with this 4 vector they call mom energy. It's not easy to pronounce, but mom energy. If you violate momentum in one frame, you definitely will violate energy conservation in another frame. And many people, it's just beggars belief. These are sacrosanct laws of physics. They're not prepared to believe. So maybe I'm a little bit conservative. Maybe I'm a little bit in awe of big science and the existing science base. But if you want to present your ideas, if you start talking wacky stuff like that, they'll show you the door. So in my humble way of doing things, I try to make the presentation as conservative as possible. Now let's talk about that list. Let's move on to Ampere longitudinal forces, or the Lorentz force, which is, unless someone tells me differently, is the same thing really. What Ampere called his longitudinal forces seem to be what we call Lorentz forces. There has been some suggestion that the Lorentz force might be a candidate for making a reactionless drive or a propellantless drive. It seems to be, if you look at this image of a railgun and you work out the forces, the red bit here, which is the sliding device propelled by the forces, doesn't seem to react against anything. But it's not true. It's a deception. You can work out the forces from the Lorentz law and so forth. What's really happening is there's a reaction in this area, counter reaction. This length of wire around here is the counter reaction. But there's a graceful way of explaining this. And that's if you consider the flux through this area. And because the flux starts out as 0, goes to something, then returns to 0, you know that you're not violating conservation. I'll give you some time to think about that. After, you can look at the slides and so forth, but that's not a candidate. The Lorentz force is not a candidate. Now, something else which seems kind of weird, the Einstein-de Haas effect, where if you have a magnet, and we know that the magnet has internal spins, yes, and it's very strong in the ferromagnetic case. And to make a magnet, you magnetize the sample, the spins line up, they kind of get pinned in place. You can talk about the exchange force or vice force and so forth. The spins get lined up and you have an overall magnet. Now, the spin is angular momentum, exactly the same units. So if you go from, say, something which is paramagnetic or superparamagnetic, and the spins are random, and the angular momentum of the whole system is 0, if you magnetize it, the whole body will start to rotate very slightly. But this looks amazing. Maybe you've got something which seems to violate angular momentum. Not the case. Angular momentum is conserved. When you take the magnet off, it's going to revert back to how it was before. This is not a good candidate. You can't use this one. Okay. So we'll move on to the Poynting vector, which is an expression of the flow of electromagnetic energy. Now, I can direct you, not in these slides, but I can make the slides available later to someone called Kirk T. MacDonald at Princeton. And he's got a very good account there about how this Poynting vector came to be. It's something which is seen as a little bit contentious, but if you accept the simplest definition works without adding on quirks, without adding on things which aren't Lorentz invariant and so forth. So let's work with the simplest definition. You start from the continuity equation, and all this is saying you've got a region of some internal energy. Oh, excuse me. Trouble being in this editing arrangement here. You've got some region which has internal energy on the left-hand side. You've got a term which describes that flow of energy. And then you've got an area where you've got work, force times velocity. You're doing work, you're either absorbing work or generating work. When you just plug in the usual formulas for electromagnetism, you come up with this term here, which is called the Poynting vector. So that describes the flow of electromagnetic energy. Great, let's have a look at the left image. Makes sense. There's a transverse electromagnetic wave. Just plug your values into this formula here, and it makes sense. The Poynting vector is going in the direction of the wave. You know, hooray, that works. If you move your vectors around to the next segment of the wave, still points in the same direction. That seems sane. Let's discuss a simple circuit with a battery and a resistor. It's a little bit weird. You've got, you can see your vectors there. You've got the electric field. There's the battery, there's the electric field. There's a magnetic field going around the wire. And the Poynting vector points out into space. It's a little bit weird, isn't it? Because you'd think that the power generated would be going along the wires. Seems to be, it's given an alternative picture, because if you look up here, this expression for the work done, you've got your Lorentz force dot the drift velocity. So obviously the cross term would go out. You take a cross product of a with the same vector, it's going to go out. So not surprisingly, you're just getting the usual Ohm's law thing here. Yes. So that works out. You've got two ways of describing it. So either you can say the energy is flowing through space between the wires, or it's flowing along the wires. And when you come down to the resistor, the energy is flowing into the resistor from space, or it's coming down the wires. So even though it's a little bit strange, it still looks like it's working. So let's take it over to the last diagram on the right, where people were seriously questioning the concepts here. And I think Heaviside is the first one, excuse me, excuse me, Heaviside is the first one to bring this up, but most people know it from the Feyman lectures, where he talks about a charged particle next to a magnet. And if you work out the Poynting flow, it's a static situation, nothing's changing, but apparently is a flow of energy. And he described this as just nuts. I think it was one of the expressions he used. You might know of this from his Feyman lectures, where he puts up a thought experiment to describe how, if it's true that there's electromagnetic momentum, this disk would rotate. And I'll just give a brief overview of what's going on. You've got this disk, obviously it's on dual bearings or somehow suspended in space. Around the edges are electrical charges. So you've got a radial electric field, and it's radiating out from the charges. And in the middle, you've got a coil, which you switch on. So his question was, what would happen when you switch the coil on? And what happens is that this starts to rotate. starts to translate, angularly translate. When you switch it off, it will stop translating. It will stop moving. How is it doing this? Because it's not reacting against anything, right? He thought it was all nonsense. But a team, Graham and Lahoz, did the experiment in 1980 and they found it to be true. So before we go on to talk about that particular device, just a little bit of background about the electromagnetic field, which will come in useful. You can find this stuff on my propulsion papers. It's in the appendix. So let's talk about quantizing the electromagnetic field. But the reason why it's relevant. Yeah, you won't really find the reason for this just in classical physics. So the usual route is that you've got the classical solution to the wave equation with the vector potential. Fourier modes, you get the Fourier modes of the field. You can use that potential to find the magnetic and the electrical fields. Put that into the classical Hamiltonian, and then you, by analogy, compare the classical Hamiltonian to the quantized Hamiltonian of simple harmonic motion. And there's extraordinary resonance there, I say, between the two. You can pull these concepts over and see that the Hamiltonian of the classical field looks like a simple harmonic oscillator. And then you just pull out the momentum operators and you relate them to the creation and the annihilation operations, which are just saying that when you create a photon, or they're also called ladder operations. When you create a photon, you do one operation, you created one photon, do it twice, you've got two photons, or if you annihilate, you've got one photon, then you've got 0 photons. That's all it is to it. So that's all the mathematical gobbledygook, all the steps I described on the previous page. But what's interesting, by the time you come down to a description of the momentum, you've got this half term, which is related to the uncertainty principle. So you cannot have 0 electromagnetic field. It will have a constant fluctuation. It may be 0, but it will have a variance. Sorry, I got it wrong there. It will have a variance, but it can be 0. So it means it's oscillating about the 0 point with this 0 point energy. It's also in the momentum operator. Right. So 0 point energy, it's a joke, right? It's just a mathematical artifact, can't be real. Yeah. When you do a calculation to work out just how big it is, it's enormous. I think, I can't remember, and it's some quote, I think it was from Pudov, saying that in 1 cubic centimeter, there's enough 0 point energy there to body world's oceans. It's got to be a nonsense, right? Why doesn't it gravitate? The amount of energy, why wouldn't it gravitate? Well, you might say that it's isotropic, so there's no net pull in any direction. Maybe it's related to the cosmological constant, but that's tiny. Right? Now, regarding the Feyman disk experiment, in their paper, they said it's remarkable when they're describing this flow of energy in that scenario. I'll just go back a few slides. When they were describing this ethereal flow of energy, because you have to have this angular conservation of angular momentum, so the mechanical aspects will start to rotate, and it's something ethereal rotating that you can't see. Graham and Lahoz, they wrote, it's remarkable that no known particle can be identified as the agent of the observed electromagnetic angular momentum in exchange with the mechanical detector. However, this does not imply that a new entity has to be introduced. It's already contained in the Maxwell classical equations. So they're saying the non-plus, you can't invent some new particle, to describe this, but there's something there. Now, I had a chat with Graham. He's a very, very old. He's in his 90s now, and unfortunately, Lahoz died over a decade ago. Now, he was intrigued because I put it to him that this thing he was looking for might be this 0-point motion. It's there in the mathematical description of it. So if you have this E cross B device, why not just make a linear device? You just have some arrangement of fields set up. So with your right-hand rule, you've got your electromagnetic momentum being expelled out the back, and somehow mechanical aspects go off in the other way. Should be easy to do, right? I believe the reason why you can't do that is that if you see this expression for the momentum, it's a two-sided transform. You have to sum over positive and negative frequencies. What this is saying is that when you set your fields up, you have to have a flow of electromagnetic energy come in to set these fields up. And you're summing over positive and negative wave numbers. So you're going to find that the 0-point term cancels. So you're going to find that a simple linear device won't work. Now, there's another explanation, and I've taken this diagram from one of Hal Pudov's papers. It's called hidden momentum. You can go to Kirk T. MacDonald's website on Princeton, and you'll find he does a very scholarly description of it. Also in my papers in the references, you'll find lots of descriptions of this. But the easiest one that I can think of is Hal Pudov's description. You've got a current loop. So this is an E cross B device. You've got a current loop, and you've got an E field going down, electrical field going down, and you've got the magnetic field coming out of the paper, and you've got the pointing vector pointing to the right here. So that should just go to the left, right? Well, it turns out there's an effect called hidden momentum, and it does sound like a fix. It does sound like one of these sort of just so stories, but there's very scholarly descriptions of it. But the simplest description Hal Pudov says is that because you have this potential, the potential energy of the fluid carriers, of the electrical fluid carriers, is increasing. So they're gaining mass. You know, E equals mc squared. They're gaining mass, and because of that, the momentum just happens to cancel the momentum from the pointing vector. So I believe, because of this, primarily because of the idea that you're cancelling, because you're adding wave vectors from both ends of the number line, that just static E cross B devices, which are just linear, are not going to work. But that's just me saying that the hidden momentum argument is the standard answer to this. Just loading up the next slide. So if we can't just generate linear momentum, maybe we can use something that we know works from the Graham and Lahoz experiment. Maybe we can use something which generates angular momentum and work out a way of turning that into linear momentum. Let's just take a look at why the angular momentum device, the Feyman disk, works. It's a static electrical and magnetic field. It literally will turn just from static fields. Now, the hidden momentum argument doesn't work here, because if you look at the E field from the electrical field, I keep calling it E field, if you look at the electrical field from all these spheres, it's uniform. It's uniform across the coil. So there's no hidden momentum argument because they're all at the same potential, right? Now, if you use my argument about the momentum, when you look at it in the quantized sense, what I'm saying is that because it wraps round, because you're path, your path of integration would be a loop. There's no beginning or end. It's not like the linear device where you have, when you do the Fourier transform, you know, effectively you have a source at plus infinity and a source at minus infinity, and you're describing waves coming from both directions to build up your waveform. With this case, because it's a circular path, it's a one-sided transform. And it so turns out that when you do a one-sided transform, the half sticks around. It's telling you something. It's telling you that you can utilize this zero-point energy. So how could we build a net propulsor from this? Something which gives you a net effect. This is what will happen if you turn on the magnet. What happens, you'll get a transient electrical field circulating around the solenoid, the magnet, which acts upon the radial balls. And when you turn it off, you get a transient circular electrical field acting in the opposite direction. So the thing can only translate, really. Yes? Turn the field on, it will spin around a bit, turn it off, and it will come to a short again. Come and stop turning again. It's a small effect as well. You'd really want to have it in a cyclical manner where you can have lots of this happening per second, and it all builds up into one great big shove or torque. Now, also what I believe here, now Puthoff did a proof for the linear case, which I didn't include. I took a slide out at the last minute, thinking it would just confuse the issue. He had a basic argument where for the linear case, where he's saying you're integrating this E cross B term over a cycle, and because the start of the cycle is the same, the integration limits are the same as just before the start of the cycle, the end of the cycle, going on to the start of the cycle, you have two terms cancelling. And he was quite unequivocal, where he thought there's no means at all of cycling the fields. This is an alternative proof he gave to me of generating net thrust. That was the linear case. It might be different here. I left the slide out. I took it out at the last minute. But the difference here is this radial term. That P there, that's the momentum, the linear momentum of the Poynting vector. That would contain your E cross B term. The R term here is the savior to this arrangement, because you can say that you're taking the radius of your effect, you're taking it to 0 at the end of the cycle, so you can get net effect. Now, this is what I propose. This is the electrical dual of the Feyman disk. So you're just reversing everything round. So where you have electrets and magnets, you turn it round so you have magnets and electrets. Now, the reason why I would prefer this arrangement, because usually when you work with magnetic fields, is usually a lot more force. Yep. Now, what I propose here is a system of these L-shaped devices, which are ferromagnetic material. Yes. Now, they're shaped in this way. So why shape them in this way? Well, it turns out that if you're going to have an electrical field going down through the page, and you've got your magnetic field going radially, you're going to find that your Poynting vector is circulating radially, not radially, actually, around the axis. And we know that the effects occurs with these pole pieces here, that the fields generated from the change in, when you switch the, in this case, the capacitors, it will be the capacitor, I'll come on to that, it's going to push, excuse me, it's going to push against these outer pole pieces. So that's a plan view. I've got a cutaway diagram here showing that on top and on bottom, you've got the capacitor disk. And in between these pieces, you've got high permeability material to help you with your help you with your electrical field. Now, the pole pieces themselves are magnetized and can be cycled. And your cycling is going to be the reverse. What you do here, electrical, then magnetic field. You switch on the electrical field and you switch on the magnetic field. With the electrical dual, the magnetic field on first and the electrical field off. Now, I believe that what's going to happen if you cycle in this manner, that disk is going to spin up and keep spinning up. Yes? So the question then is, if you can make something which generates net angular momentum without pushing against anything apart from the field itself, how can you turn that into linear momentum? Well, I believe it might be something like this. It's a bit like a conveyor belt, a belt conveyor belt. You've got rotating rollers, and they're able to send the belt forward. So what I suggest we do is that we put these angular momentum generating devices onto a plate. That's just a label. It doesn't mean any kind of device. This rectangular box with plate on it. It's just a label. But you put the devices onto a plate. Obviously, they're going to put the plate in some kind of tension, but the forces resolve. When you work the forces out, it resolves that you get a linear thrust. So I believe that might be possible. And when you put the numbers in, you're going to get forces of the order of this equation. So you could make a microwave cavity out of these devices rather than sort of discrete components, as you saw on this slide or even this slide. So let's just say that somehow we find this. So instead of having bulk inductors and bulk capacitors, it's some kind of microwave cavity. Let's just argue that the field is about 1 Tesla. The electric field is about 30,000 volts per meter, and you're cycling at, say, 10 gigahertz. It would turn out that you could get something like 2.6 tons from a volume of a meter cube. If this is correct, if it's correct, and let's say go up to optical frequencies, and you can see the numbers there. Well, fantastical numbers. You know, you're talking more than the thrust of a Saturn V rocket. But if it's true, that's a lot of engineering there. That's the kind of promise that this technique might have. So to dot the I's and cross the T's when one's talking to one's colleagues, you know, academic colleagues, they say, oh, we can see all that, it looks nice, but where's your momentum going? Yeah, you're somehow dumping momentum. I just don't believe it. So I have to set up a model to somehow explain how this might be possible. And this is what I'm working on at the moment. It would be better to work on some of the experimental aspects. I'll get onto that. I'll get onto that in due course, but I want to look at the theory first to make sure I'm not wasting my time. So what I'm trying to do is look at the field and describe it as an ensemble of oscillators. Yes, and they've got this 0 point term. So there's mass energy in the field, all right? So by analogy, if you take a hydrogen atom, the electron around the nucleus is in simple harmonic motion, a version of simple harmonic motion. It has 0 point energy too. And you can move a hydrogen atom about, you can translate it in space. So I'm saying by the same token, these modes that make up the electromagnetic field, they have a 0 point term, why can't you set that in motion? So when you press against the field, you're effectively, even though it has a very huge mass, you can move those electromagnetic modes that describe the field. Now, by analogy again, so you've got a collection of hydrogen atoms. They're going to experience what they call London forces, van der Waals forces between them from momentary fluctuations in the electron crowd around them. So they are linked together. Yes, they interact. So I'm saying by the same token, maybe it's possible that all the modes of the electromagnetic field can interact by this zeropoint fluctuation. So if you take a single mode, as it's fluctuating, and remember it has a variance, as it fluctuates on an individual mode, as the electrical field fluctuates, it's going to temporarily look like a dipole. It's going to go plus and minus, and it will switch around and do that randomly. All the other modes are doing just the same thing, and you'll have an effective field around your mode. So what I'm trying to say is that the field, the electromagnetic field, even though it's ethereal, it's beginning to look a bit like a supersolid, a superfluid or a supersolid. It's like a lattice, yes? And the reason why I put the appendage super on the front, because it just simply flows through us with no friction, yes? Although some will say it's a source of inertia, but it's not like a normal fluid, yeah, where you suffer viscosity effects and so forth. So I'm working on the paper at the moment. This is all very highfalutin stuff and probably won't even be regarded. But I believe that you can describe it almost with mechanical effects. So you can predict a heat capacity for it. You can predict the speed of sound for it, which would be the speed of light. Even longitudinal waves. You can describe second sound in it. And most importantly, dissipation. So someone wants to know, okay, I can see your device, purportedly you say you're pressing against the zero point of the field. Show me how that's a dissipative effect. So I'm able to show how momentum can go to the field and become thermalized, randomized, yes? And then that would complete the proof that you're pressing against something with substance. How are we doing for time? I'm just going to take a quick time check. 45 minutes. Okay. I'm going to move on to other projects of mine and other people which might be pertinent to UFOs or UAPs as they're calling today. Can't spend too much time on them because they're really other presentations in themselves. Now I'm working on an entanglement communication system using quantum entanglement. And the reason why that's interesting, apart from sending information, nothing which is massive. Information has no mass energy, but you can send information faster than light for that reason. It breaks the space-time construct. You know, we're looking at new propulsion devices. Maybe we need to be looking at ways around relativity theory. And got another project to do with thermoconversion, which is greater than Carnot efficiency. And there are counts from people who have been contactees saying that these UFOs, they run cold. They've got a much more sophisticated way of energy conversion than we do have. So it's kind of relevant to today's talk. Let's have a quick look at the entanglement communications project. In the middle here, or near enough the middle, you have a source that generates two photons, and they're what we call entangled. They're correlated, yes? They share a joint wave function. So if you measure one, it's going to affect the wave function of the other. They have statistical correlation. Send one off in one direction to the left, send off the other to the right, and you have an interferometer setup. Now, what you can do when you measure on the left-hand side, you collapse the wave function from being coherent, from being a pure state into a mixed state. And the right-hand side, excuse me, will pick up this change. If you have a pure state, you'll get interference. If you have a mixed state, you won't get interference, and the detector can pick this up. Now, I've been around the block with many academics with this, and I'm not feathering my own cap, but the best ones have said things like, of course it's possible, of course it's correct, but they don't stand by you. I've got to do the experiments at some point. I think I told you what happened to me a few weeks ago with some university which is meant to do the experiment for us. They just ran off with the money. That was very nice of them. What it comes down to, though, is this idea of the evolution of a joint wave function. Now, on both sides, free space and the interferometer, they're what they call unitary operations. They don't affect the wave function at all, apart from add on a phase. Yes? And the phase is just the essence to say that time has flowed, time has ticked on. You've got a phase on, just like a wave. When you send a wave, when you measure it later, it will have a different phase. So that's all unitary operations do. Yes, they don't affect the wave function, they just add on a phase. Now, what I'm trying to say to these people who cite to me and say the no communications theorem, and saying, well, if by solely regarding, even just thinking about one system of a joint system, I have to take the partial trace, and so take it from being a pure system into a mixed system, well, entanglement wouldn't even exist. This part here, where it's traveling in free space, am I meant to take the partial trace here? You wouldn't have entanglement. If you have a unitary operation, which is this interferometer, up to the point where the detector measures, this is not doing anything to the wave function. I do not have to take the partial trace through the interferometer. Some of them are getting this. Now, as regard the entanglement signaling, what's the speed of it? Well, as far as we know, Alan Aspect did an experiment in 1980. Well, no, sorry, Zibindan did a recent experiment in 2008 where he measured the speed of wave function collapse as at least 10,000 times the speed of light. So this is not to say that he sent any information. What he did was showed after the fact correlations. So say you've got the system I discussed earlier with the two photons in what they call HV polarization, horizontal and vertical polarization. When the system's not measured, it has an indeterminate angular momentum. Polarization equates to angular momentum. When you measure it, it goes into a very definite state, such that the sum is always the same as the original angular momentum of the system. So if you measure horizontal on the left-hand side, you'll measure vertical polarization on the other side, and vice versa, vertical on one, horizontal on the other. Now, if you imagine a ticker tape running as you're measuring the outcomes of your measurement, it always lines up. Horizontal, vertical, vertical, horizontal. And this experiment was done to over 10 standard deviations, yes, to show that it's always true. And it just comes down to conservation of probability, right? So we know that at least after you've done the experiment, when you look at the ticker tape of the outcome of the experiment, over space-like separations, everything matches up. And to do that, some effect is passing between the stations at the end of the experiment, but it's going at least 10,000 times the speed of light. So to me, this is just a smoking gun. This is just saying relativity is flawed, and your way of getting around it, trying to save relativity, the no communications theorem, is wrong. You take the partial trace after joint evolution, not before. Okay, I'm not quite sure how well I'm getting that across, because it is really, it's a whole presentation in its own right. Now, this is what I came up with to explain how the space-time narrative breaks down. You know the usual space-time diagram, and it's a hyperbolic, what they call hyperbolic motion. Yes, the Lorentz transform. Your axis of the moving system deviate from the right angle. So you get a new, when you look at events of a moving system, the prime system, the axes aren't at 90 degrees. And when you project onto these axes, one of the things you find is that there's no simultaneity. Yes, simultaneity. Right, that's one of the features of relativity. You can't say events are the same in all systems. You can't say there's any synchrony between events. But if you look at the faster than light system, it appears that you can do this. And the way to do that is to change the transform. You drop out all of these retarded time terms. So here's a relativistic transformation between frames. And these terms are purely the time it takes for a light speed signal to go from one point to the other. If you're sending information faster than the speed of light, you knock them out. And they're your new axes. So you preserve simultaneity. Okay, let's move on to the other project, and that's to do with thermoconversion. It's another controversial one, but I have to say, Professor Daniel Sheehan, he's a really good chap, stands by people working in this field, yes, and he publishes in the top journals, yes. So he's given the whole area credibility. You don't tend to get laughed out of the room anymore. Now, he uses the term Maxwell zombies. We know about Maxwell demons, the idea that once you have a system which is at constant temperature, heat energy is just a random distribution of the energies, of the kinetic energies, of the potential energies, and so forth. So because it's uniform everywhere, you can't run a heat engine in it, because normally heat engines would run via gradient. If you had a Maxwell demon, this hypothetical little being, which is able to sort this random distribution, so you could sort your hot molecules onto the left, say, and your cold molecules onto the right, you could run a heat engine. And then people will laugh at that and say, well, that's perpetual motion. Yes, they're very simple thinkers. They haven't really thought about it. There's no perpetual motion apart from microscopic perpetual motion. If you could build a Maxwell demon, it would fall to pieces someday. It would run down. It's not perpetual motion. It's heat reuse. It's heat reuse. That's what it is. So the idea that this demon has to be intelligent, the Maxwell demon, is not true. Sheehan calls them Maxwell zombies because they're just autonomous processes. There's no fault involved. It's just simply processing information. Here's a hot molecule, put it that way. There's a cold molecule, put it that way. So what I've looked for in my research is on this, and where these ideas come together, is that I'm working with phase changes. So first order and second order phase changes. First order phase changes are things like evaporation or melting. Yes. So you have your Maxwell-Boltzmann distribution, and you can draw a line at the top end of the distribution saying that any moieties with energy greater than that will phase change, will convert from water to liquid. It's a sorting process. It's a Maxwell demon or Maxwell zombie process. It's also the same with second order. Second order phase transitions are gradual phase transitions. Things like magnetizing a magnet. A lining spins up gradually. Yeah, they're called second order phase transitions. You can find all this stuff on the website. But I came up with two scenarios. I did research in this, ran out of money. I was working on the ferrofluid system. It so turned out. Lovely chap, great chap, Professor Grady. He wanted $500,000 for research, so that kind of I was only left to doing simulations. Let's take a look at the first order system. Yeah, I'll tell you what this is. This is a column with a reverse osmosis membrane at the bottom, and you've got a hygroscopic liquid, and around it you've got an atmosphere of water vapor, just water vapor. Keep it simple. The water vapor will condense at the top, and it will build up a head of pressure, so that at the bottom pure water flows through the reverse osmosis membrane. And of course, when it flows, it's got potential energy. It can run a device. Excuse me. So it's not practical, but it's a kind of what would you call it? A paradox. A paradox. Well, I worked on the second order system because it is more amenable to engineering, and I worked on the system where you were dealing with ferrofluid and you had a magnetization demagnetization cycle, which is a little bit too technical to go into here. It would take too much time, but you could convert heat energy directly into electricity. Yes. And not just do it at high efficiency. You could have a closed isolated system where it would just go round and round. So you convert your heat energy into useful energy, let that useful energy degrade back to heat again. It would just go round and round and round until the device failed. And it's not perpetual motion because the device does fail in the end. It does wear out in the end. But people who don't want to push the boundaries of research forward, who can't follow a logical argument, or maybe they're just scared or have cognitive dissonance, they don't look at these things. But we don't care about them. But there's an awful lot of them in the university system at the moment. A lot of them are scared to do original research, so it's left to people like us with our resources and with our spare time to look into these things. So, Tim, that brings to the end my presentation. I hope it was coherent enough. Okay.
Absolutely. Remi, thank you. But let me do this. The first thing I want to do is I'm going to stop your screen share, and I want to put this on gallery view. And everyone, please give Remi Cornwall an enormous hand for a remarkable presentation.